I'm Mike Mathias, Project Manager for Engineers Without Degrees. I'm here at Lake Murray. We have a conceptual project we want to share with you, rain harvesting project at Lake Murray. First, I'd like to introduce the rest of the team.
Hi, my name is Taylor Brown. I'm a civil engineering major.
Brian Schroth, civil engineering major.
Diana Padilla, civil engineering major.
Scott Fleming, civil engineering major. Daniel Vega, civil engineering major.
Lake Murray water harvesting. In this presentation, we want to explain to you what the goals are of the project, the need for the project, how we think this project can work, the equipment involved, and also the feasibility of the project and what benefits the city and the people of San Diego can expect.
California's current drought has been billed as the driest period in the state's recorded rainfall history. Due to the recorded drought, especially on the western states and western provinces of the United States, harvesting water could be a great solution to improve water quality demand.
Our goal is to increase local water supply in order to offset the cost of imported water for the city of San Diego, as well as keep our school team practicing for Pacific Southwest Conference.
Woo! Go SX!
Let's just assume that this is the San Diego water supply. 20% of our water comes from local water sources, and 80% of our water is imported. So the main purpose of our project is to minimize the amount of water that it's imported and to maximize the local water resource.
Hi there, I'm Daniel, and I'll be speaking about the existing conditions of Lake Murray. Its surface is about 171 acres and about 96 feet deep. The reservoir holds about 4,700 acre-foot of water. The hydraulic study area, which is all the area all the way over there, it's about 2,000 acres. And it interpolates between open space and low density dwelling units for the runoff coefficient. According to the hydrology manual of San Diego County, the rain intensity for a 24-hour event in an 85th percentile isopluvial map is about 0.65 inches. And it all drains into a concrete channel that flows from the east side of the lake to the west side of the lake. And at the very end of the channel is where our study area is at.
In 1950, the city of San Diego took over operations of the dam, and in 1961 took ownership of the dam. Immediately adjacent to the dam is the Alvarado Water Treatment Plant, which is one of 3 water treatment plants in the city of San Diego, and it is actually the oldest. It has a capacity to treat 121 million gallons a day. Awesome.
Here we are at the site of our proposed improvements for our project. Located here is the existing channel that flows downstream over the spillway and into Alvarado Creek. Our design is to have 2 water quality sensors located upstream of a diversion box with 2 slide gates, one of which will open, allowing clean water to flow through a box culvert to the other side of the road and dispense over energy dissipators into Lake Murray.
So Scott just discussed the proposed site improvements. I'm going to continue on and go a little bit more in depth on the technology that we're going to apply on our project. The 2 water quality sensors are going to detect the water quality that is coming downstream from our watershed. Once the water quality sensors determine that the water is acceptable, the signal is going to be relayed to a control box, which is going to be on site, which is powered by solar powers, and they have a battery charge to provide power to the slide gates, where are controlled by actuators. At that point, the water quality sensors will tell one slide gate to close and the other one to open, and vice versa. The slide gate that's open is going to be allowing water to bypass the lake and continue downstream when the water is not at acceptable levels. When the sensors determine that the water quality is acceptable, the slide gate will close the channel, and I'll open the diversion box, will allow water to go downstream, diverted into the culvert into Lake Murray. At any given time, the water quality sensors determine that the water is no longer acceptable. They'll be reversed, closing the slide gate to the lake and opening the slide gate to continue downstream into Alvarado Creek and not allowing dirty water into Lake Murray.
First flush, as the name implies, flush off the first water of the storm before it enters the storage tank or the reservoir. This is the water that could be the most contaminated.
Water quality is a big consideration for this project. After all, Lake Murray is a drinking water reservoir for many San Diego residents. Because of that, we've provided flexibility in the project with 2 water quality sensors to help water treatment operators regulate the quality of water discharging into the lake. The water quality sensors that we're proposing can measure a host of different constituents, including total dissolved solids, dissolved oxygen, and turbidity, to name a few. The water treatment operators will have the ability to determine what threshold each of those constituents qualifies as a acceptable water, and only then will the water be allowed to discharge into the lake.
So to elaborate on what Brian discussed, here's a 3D model on our channel diversion system. In this view, you'll notice the channel is in its dry weather or first flush position. The gates are positioned in such a way that the dry weather flows through the system down into Alvarado Creek as the channel was originally designed. Now you can see in this version of the model that the gates are reversed, which is a result of the sensors that you can see positioned upstream sending a signal to the system that the water is an acceptable quality to be allowed into the lake. In this configuration, the clean water flows through the box culvert under the road and then flows over a riprap energy dissipator and then into the lake. So one of the big questions is this project cost effective? Well, that's really based on 2 different factors. On one hand, we have our construction cost estimate. And on the other hand, we have the amount of water the city will be able to save annually, and that converted into a dollar value. So as you see on the table, we've estimated our construction cost to be roughly $762,000 a year. And we can compare that to the amount of water that our new system will be able to save over the existing channel. We've calculated that out to be roughly 279 acre-feet a year, which would bring roughly $335,000 of revenue to the city each year. Given that number, we've calculated that the project should pay itself off in roughly 2.3 years. So in one word, yes, it is cost effective for the city to build this project. So in conclusion, we showed you how this project will fit with the existing channel and how we came up with a simple design that sensed when the water was acceptable to be diverted into the lake, and we proved that the project would be cost effective if the city were to decide to build the project. Thank you so much for watching our video, and we hope you enjoyed learning about the Lake Murray Water Harvesting Project.